Hello guys and welcome back. Today is part 10 of AC control methods. And today's topic or subject is going to be synchronous automatic motor starter. We're going to talk about how the out-of-step relay protects the starting winding of a synchronous motor. We're going to talk about the action of a polarized fuel frequency relay in applying and removing DC fuel excitation of a synchronous motor. We're going to talk about how to connect synchronous motor and controllers which use an out-of-step relay and polarized fuel frequency relay to achieve automatic synchronization. And we're going to recommend some troubleshooting techniques and solutions for problems. An automatic synchronous motor starter can be used with a synchronous motor to provide automatic control of the startup sequence. That is, the controller automatically sequences the operation of the motor so that the rotor field is synchronized with the revolving magnetic field of the stator. There are two basic methods of starting synchronous motors automatically. On the first method, full voltage is applied to the stator winding. In the second method, the starting voltage is reduced. The commonly used method of starting synchronous motors is the cross-line connection. In this method, the stator of the synchronous motor is connected directly to the clamp distribution system at full voltage. A magnetic starter is used in this method of starting. A polarized fuel frequency relay can be used for the automatic application of field excitation to a synchronous motor. Rotor control equipment. Field contactor. The field contactor opens both lines to the source of excitation. During starting, the contactor also provides a closed field circuit through a discharge resistor. A solenoid-operated field contactor is similar in appearance to the standard DC contactor. However, for this DC-operated contactor, the center pole is normally closed. It is designed to provide positive overlap between the normally closed contacts and the two normally open contacts. This overlap is an important feature because it means that the field winding is never open. The field winding of the motor must always be short-circuited through a discharge resistor or connected to the DC line. The coil of the field contactor is operated from the same direct current source that provides excitation for the synchronous motor field. Out-of-step relay. The squirrel cage winding or starting a motor cell winding will not overheat if a synchronous motor starts or accelerates and it reaches synchronous speed within a time interval determined to be normal for the motor. In addition, the motor must continue to operate at synchronous speed. Under these conditions, adequate protection for the entire motor is provided by 3 overload relays in stator winding. Squirrel cage winding, however, is designed for starting only. If the motor operates at synchronous speed, the squirrel cage winding may overheat and be damaged. It is not unusual for some synchronous motors to withstand a maximum lock rotor interval of only 5 to 7 seconds. An out-of-step relay, OSR, is provided on automatic synchronous starters to protect the starting winding. The normally closed contacts of the relay will open to the energized line contactor under the following conditions. First, the motor does not accelerate and reach the synchronous point after a preset time delay. 2. The motor does not return to a synchronized state after leaving it. 3. The amount of current induced in the field winding exceeds the value determined by the core setting of the out-of-step relay. As a result, power is removed from the stator circuit before the motor overheats. Polarized field frequency relay. A synchronous motor is started by accelerating the motor to a high speed as possible from the squirrel cage winding, and then applying the DC field excitation. The components responsible for correctly and independently applying and removing the field excitation are a polarized field frequency relay and a reactor. The magnetic core of the relay has a direct current coil, an induced field current coil in a pivoted armature, to which contacts are attached. Coil C, for example, is connected to the source of DC excitation. This coil establishes a contact magnetic flux in the relay core. This causes the relay to be polarized. Superimposed on the magnetic flux in the relay core is the alternating magnetic flux produced by the alternating induced rotor field current flowing in coil B. The flux through armature A depends on the flux produced by AC coil B in DC coil C. Coil B produces an alternating flux of equal positive and negative magnitude each half cycle. Thus, the combined flux flowing through armature A is much larger when the flux from coil B opposes that from coil C. The flux from coil B opposes the flux from coil from DC coil C, resulting in a strong flux being forced through armature A of the relay. One half cycle later, the flux produced by coil B reverses and less flux flows through armature A. This is due to the fact that the flux from coil B no longer forces as much flux from coil C to take the longer path through armature A. The resultant flux is weak and is illustrated by the small upward shaded loop. The relay armature opens only during the period of the induced field current wave, which is represented by the small upward loops of the relay armature flux. As the motor reaches synchronous speed, the induced rotor field current in relay coil B decreases in amplitude. A value of relay armature flux upward shaded loop is reached, at which the relay armature A no longer stays closed. The relay opens to establish contact S. DC excitation is then applied at the point indicated on the induced field current wave. Excitation is applied in the direction shown by the arrow. The excitation is opposed in polarity to that of the induced field current at the point of application. This requirement is necessary to compensate for the time needed to build up excitation. The time interval results from the magnetic inertia of the motor field winding. Because of the inertia, the DC excitation does not become effective until the induced current reverses point zero on the wave to the same polarity as the direct current. The excitation continues to build up until the motor is synchronized, as shown by point M on the prairie. DC excitation is applied to the core of the relay at the instant the synchronous motor is started. When the stator winding is energized, using either full voltage or reduced voltage methods, line current is allowed to flow through the 3 overload relays and the stator winding. The line frequency currents are induced on the 2 electrically independent circuits of the rotor. First, the squirrel cage or starter winding, and second, the field winding. The current induced on the field winding flows through the reactor. This device shunts part of the current through the AC coil of the frequency relay, the coil of the out-of-step relay, field discharge resistor, and finally to the normally closed contacts of the field contactor. The flux established in the frequency relay core pulls the armature against the spacer and opens the normally closed relay contacts. As the motor accelerates to the synchronous speed, the frequency of the induced current in the field windings diminishes. There is, however, sufficient magnetic flux in the relay core, called the armature against core. This flux is due to a considerable amount of induced current forced through the AC core of the frequency relay by the impedance of the reactor and high slip frequency. At the point where the motor reaches its synchronous speed, usually between 92 to 97% of the synchronous speed, the frequency of the induced field current is at a very low value. The reactor impedance also is greatly reduced at this low frequency. Thus, the amount of current shunted to the AC coil is reduced to the point where the resulting core flux is no longer strong enough to hold the armature against the spacer. At the moment that the motor speed and the frequency entirety of the induced current are most favorable for synchronization, the armature is released. The relay contacts close and the control circuit is completed to the operating coil of the field contactor. DC excitation is applied to the motor field winding. At the same time, the out-of-step relay and discharge resistor are de-energized by the normally closed contacts of the field contactor. An overload or voltage fluctuation may cause the motor to pull out of the synchronism. In this case, a current at the slip frequency is induced in the field winding. Part of this current flows through the AC coil of the polarized field frequency relay, opens up the relay contacts, and removes the DC field excitation. The motor then automatically resynchronizes if the line voltage and load conditions return to normal within a preset time interval, and the motor has enough pull-in torque. However, if the overload and low voltage conditions continue so that the motor cannot resynchronize, then either the out-of-step relay or the overload relay activates to protect the motor from overheating. Thank you guys for watching. Again, please like, share, subscribe, and feel free to comment. See you in the next one.